In the next 10 or 20 minutes, we'll be spending more time about understanding how Earth observation data, or in other words, satellite images, can be used to quantify and measure economic activity. So let me start with my background, which is, so I am the CEO and co-founder of Think Evolve Consultancy. We help startups and enterprises formulate their AI/ML strategies. And we handhold them throughout the entire data science cycle, from business ideation to model training and deployment. We are trying to build an IP-focused organization by submitting US patents and publishing research. If post this talk, if you have any doubts or you want to know more about our work, you can reach out to me via LinkedIn or send me an email, or you can also follow our company page on LinkedIn. So cool. So when you say satellite images, we always use proxies to identify, to measure that economic, whatever economic indicator value that you want to find out. So if you remember a few years back when COVID-19 pandemic hit us, it spread with alarming speed. And to stop it as an emergency measure, a lot of governments instituted complete lockdowns. But this lockdown also led to an economic collapse and a contraction in GDP. But being able to measure such contraction in real time can provide policymakers and businessmen with a useful tool to quickly make course corrections. So during this talk, I will give you a broad overview of the various methods which are available and which we can leverage using open access Earth observation data and quantify this impact on the world economy. So for measuring, we usually use proxies like measuring air pollution or using sensors to measure the quality of water. We can also use high resolution satellite images to measure distribution of cars in a parking lot, or by counting the number of parked aeroplanes. Highways are considered as a lifeline for most economies. We look at an innovative technique to measure the number of moving vehicles on roads. Quality of life is also an important indicator of the inclusiveness of economic prosperity. I will show you how we can use air pollution or the quality of river water using low resolution satellite images. Although many of these indicators computed through remote sensing can also be measured through traditional data sources. But satellite images is more versatile. And with little effort, this monitoring can be extended to cover the entire globe. The reason is we have a common database and input format. All that we need to is increase the computational power and satellite coverage. So this also does a good thing is that it eliminates any complications associated with data collection from heterogeneous sources at this scale. These characteristics favor the adoption and application of such systems when a fast response is critical. So this was visible during the Ukrainian crisis, which is ongoing, and the Russian invasion. This is a very good example of how we can use satellites and drones in times of crisis. So in war, both sides make claims and counterclaims. So how can we penetrate the fog of war? This is where satellite imagery and drones come into play. They can provide a bird eyes view and provide strategic analytics. So what you see here are a set of images from Maxar technology, which gives you a hint of their capabilities. So on the left top hand side, you see a multi-spectral imagery, which shows fire burning at the Antonov International Airport in Ukraine. This is from March 11th. The image from in the bottom right is the infamous bombing of the Mariupol Drama Theater, which shows the extent of the damage over there. Mostly, a lot of civilian infrastructure has been destroyed because of this bombing. And this, if you can look at it, this shows a change in the changes in the infrastructure and how a properly good place has been destroyed. We can use satellite images to identify the Russian convoy that was moving towards Kiev. There are other things which this intelligence can also be useful in providing alternative safe routes for evacuating refugees. So some of my tech bros are working to elevate this situation and helping using their technology jobs, tech jobs to help it out. And you can also sign up for a pledge on Tech to the Rescue or Tech for Ukraine. We have another charity called Ukraine Now, which is run by a friend, Arthur Killian, and who is also working tirelessly to help these refugees escape from the hellscape. So yeah, so Slava Ukraini and glory to my friends in the community. I hope this this time will pass out. So generally, when we work with data science, we talk about a hypothesis. So our hypothesis is that economic activity can cause pollution. And when there's a successful lockdown, it leads to a decrease in the pollution because there is less economic activity. For example, if you look at, sorry, so if, for example, when I say economic activity, this is mostly in terms of industrial activities like manufacturing, construction, and mining. So, or even transport. So by counting the trucks on roads or highways, trains in railway stations, containers in dry ports, these are possibilities of economic indicators, but they can also point out supply chain problems. This pool of indicators can vary according to the local interest of each city. And this information, you can compose it as a dashboard to help decision makers in spotting situations that demand immediate attention. So this is a very simple technique that we are used where we have used Sentinel 5P data sets. Sentinel is a set of satellites which have in orbit, polar orbits around the Earth. And they use multiple sensors to capture different types of data sets. Now, Sentinel 5P captures a lot of data regarding aerosols, carbon monoxide, nitrogen dioxide, CHF values in the atmosphere. Using these images, we can actually identify any kind of anomalies or spikes which are taking place. And then we can use high resolution imagery to go deep down into the area of interest and see what is causing that changes. So what you see out here is a composite image that we have created using Sentinel-5. As I said earlier, that Sentinel-5 measures NO2 levels. But NO2 is a result of industrial activity. Okay, so basically burning of fossil fuels. So if you look at here in these images, this has been taken on April 30, 2019. You see red spots around major industrial belts like the Delhi Ghaziabad belt out here in India. We have some red spots around Varanasi and Bhilai Jamshedpur, which are major manufacturing and steel manufacturing areas in North and East India. We also see red spots over major cities like Mumbai and Hyderabad, Ahmedabad and Surat in Gujarat, and also in our neighboring countries like in Pakistan, we see around over Karachi out there. So, but when we take a similar snapshot in April 30 and April 2020, we see a significant drop in nitrogen dioxide level across the Indian subcontinent. Now you should remember, take in context that on March 15, a complete lockdown was instituted. A complete lockdown and all manufacturing activity had stopped across the across the entire continent. So this caused a significant drop in the pollution levels, and which can easily be seen from this composite image that we have taken. So we actually took this up, and then we tried to see if we can do this measurement across other countries. And we did for France, Germany, China, we did for Austria, Italy. And we found that wherever the lockdowns were strictly implemented, we saw a significant decrease in NO2 levels. But in places where the lockdown was not very strict, like in Italy, the change there was no perceptible change in NO2 levels. So this is a graph where we have tried to map up with the dates to give you context behind it. So if you see like in 13 and around March, a lot of the lockdowns were instituted in France and Germany, and there's a significant change in the pollution levels. The same thing happens with Austria and Italy, but in less degrees because we believe that lockdowns were not that strict. If you see any missing values, that is because the sensors seem to have some problems in capturing good values, and so there are some kind of missing values out there. So, okay, I think I just closed my screen. I wanted to show you another tab. Okay, so I wanted to show you the tool that we are using for creating this composer. So what you see here is an EO browser from Sentinel Hub, which is freely available and anyone can go and sign up. It basically shows you a list of satellites which you can use. And Laura, let me know if you can see the screen or it's not visible. Okay. So you can select which satellites you want to pick up and get them visualized out here. So the one that we chose was Sentinel-5P and specifically nitrogen dioxide across the years, and we'll get that information over here. And then we can visualize them on this dashboard. Cool. So as you see, these are indicators. The blue indicates less pollution, while the red will indicate higher concentration of NO2 out here. A large part of Ukraine, you can see out here if you want to measure how Ukraine looks. You have a date out here which shows on 23rd March, this is the NO2 levels over Ukraine. And you can then move back in time, say like 2020, same date. This is how Ukraine looks. So you can see a significant change. So let's go back to our presentation. So the other ways of measuring is looking at the quality of river water. So during the lockdown, there were a lot of chatter, social media chatter to say that there was spotting of wildlife in the canals of Venice. A lot of it was obviously fake news, but if you look at the satellite images, you can notice a significant drop in water pollution in the water. And there was a very simple reason for that, and that is that lockdown led to few boats in the water, which meant less pollution. Now, the image that you see out here are two images that were taken from PlanetScope satellites. And this PlanetScope works in the visual spectrum, and they have a slightly higher resolution than they have a slight higher resolution Sentinel 5P. And this, the one to the left was taken in February 2020, and the one to the right was taken after the lockdown in March. What this shows is that there's a lot of turbidity in the water, and you can also see boats which are seen as these white streaks out here. Post the lockdown, you see that the water is very clear, and there is hardly any boats out there going through the canals out there. So these, while access to such high resolution images may not be available to most of the population, but most of the researchers out there, we can also use low resolution data to identify plankton or the absence or presence of plankton or aquatic life in the water. So the next image that I will show you is of Victoria Lake in Africa. And we have used Sentinel, one of the Sentinel website satellites, which is Sentinel-2 and L2A images, where we have calculated the floating algae indicator out here. The green shows the presence of aquatic life in the lakes, in the water of the lakes. And these are all false colors. And if you look at this redness near the shore, it shows turbidity in the water, which could be because of a discharge of effluents. So by calculating these values, you can look at what is the source of pollution. We can also use a barren soil index to look at patterns of fallow patterns and crop rotation. This shows lettuce production in the US. And we can plot it across time to see how the pattern changes. A similar system can be used to look at surface water. So a good point to note out here is that we have sometimes we can see this being done with this. Ukraine has a lot of fertile soil out there, which is used for producing large quantities of wheat and other grains. The red color that you see out there is in the near infrared range, and which shows vegetation of crops out there. So these are all good fertile land, which is now under attack. So this gives you a sense of the proportion, because you can use these satellites to get these kind of insights from these images. So let me get back to the slide. And so a lot of times using forest land for development purpose is a very dicey subject, because it's very political in nature, especially for developing countries like Brazil. They need to make a trade-off between development and protecting the environment. There have been budget and political constraints which has resulted in defunding, and the number of forest inspectors in the Brazilian Amazon rainforest has reduced significantly. So this has created a strain on existing resources, which is basically means that less number of inspectors are there to cover the entire area. Now, our team, which worked at Planet Hack 2020, created a web app which could identify such logging incidents in real time. The final goal was to create a completely automated system that creates alerts on which inspectors can then act. This also makes them very efficient. Now, the other part is, whenever you look at satellite images, one of the main assumption is that it's a clear line of sight for them. So if you have something like a rain cover or a cloudy area, it is difficult for these satellites to capture these images. So that's why we use a different technology, which is called a synthetic aperture radar images, which is nothing but a radar image which is being sent out by the satellite sensors. The radar image hits the ground and then it disperses, which is then captured by the sensors. And this helps you to have an all-weather view of the ROI or the region of interest. So this is very useful for monitoring road construction, real estates, and looking at military establishment or military buildups. So here you see the area, so what we are trying to capture in these images is the dispersion characteristic of the radar. So once it hits, if it has a different, every material has a different dispersion characteristic. So if it hits concrete, you can identify that it has hit concrete. So you can understand from just by looking at the dispersion characteristic, what is the type of uh, construction material used. And by measuring it over time, you can get an idea of how much of construction is taking place. So, and because of its unique characteristics, like even if an object has been hidden from view by using a covering like a tarp covering, or by using grass or something, it still can be identified from the satellite images. So this is an image which was shared by Capella Space, which has set up a number of satellites which capture these images. And as you can see, this in February 22, they identified the buildup of military vehicles on the ground. You can see bulk surface to air missile launchers. You can see infantry fighting vehicles and possibly armored vehicles, heavy transport vehicles near the border with Ukraine. So we'll go to more state stuff like measuring car distribution using VHR imagery. Uh, a lot of times, as we have earlier discussed, airports, seaports, highways are considered as lifeline of most economies. So measuring the traffic on these roads, especially commercial traffic, has high economic consequence. And by measuring the number of vehicles on roads of industrial and commercial spots, we can know about the vitality of that region. Uh, there's a good use cases of looking at car parking lots from amusement parks or malls and identifying how many people visited it on that given day. Uh, but this requires a high resolution image, something like which PlanetScope gives, which has a spatial resolution of 30 centimeters. Using an open source model, we can identify 60 different classes of vehicle. A significant change in distribution of cars can indicate business stress and a high probability of store closures. A similar system can be used to identify parked aeroplanes. This was specifically for the COVID-19 scenario where because of because of bans in international travel, most of the aeroplanes were on the ground. You could find a lot of parked aeroplanes on airstrips. Uh, we have used a tool called as known as Spectera, where we have, which is a no-code approach to create your own detection model. Uh, so if you are someone who likes no code, you might find this a very good and easy way to build your own object detection algorithm. You need to simply upload any images and identify the area of interest, and you can train a model online. Here, as you see, is we have used two images. One is of uh, mall in Hamburg in Germany, and the other is the parking lot in the Milan Expo in Italy. We have identified a number of cars that are parked out there. Now, there are two things when researchers go. One is that, and one of the most important constraints is cost. Not many people have access to freely available relevant satellite images, which is relevant to their requirement. So I will discuss one of the use cases in more detail, and that will use low resolution images, satellite images. And we use a multi-spectral characteristic to identify trucks out there. A second use case that I'll discuss is using NDWI index to calculate the surface water changes. Let me start with the first use case, where, as we said, that highways are the lifeline of most countries. So measuring traffic on this route, especially commercial traffic, is of high economic value. So we hear what we have. So but these sentinel images have so like in the previous slide, this had a spatial resolution of 30 centimeters, which means that one pixel on this image is a 30 by 30 centimeter square on the ground. The Sentinel images that we get, which are freely available to everyone, has a resolution of 10 meters. So each pixel that you see here is a 10 by 10 meters square on the ground. Now, at this spatial resolution, it is difficult to detect an object like a truck. So what we have done is that we use a specific signature which is created by a traveling truck on Sentinel sensors. The Sentinel satellite sees a traveling vehicle in 3 times across the different spectrums. And this leaves back a distinct signature on the image. And using this signature, or identifying the signatures on the ground, we can count the number of trucks. So we have created an overview of framework of how we go about doing this, and I will cover each of them in detail. So since I have notebooks out here, but since this is just a talk, I'll just walk you through the process. Maybe somewhat next time when if we have a workshop, we can go over the notebooks in more detail. So what we are doing out here is we are selecting a region of interest for us, which is a bounding box. And this we use a tool called as Box Finder, or even on Sentinel Hub, we have a request builder, which helps you get the coordinates of this region. We have used the city of Vishakhapatnam, which is a major seaport in India, on the eastern coast of India. And hence it has a large number of container traffic. So then once we have chosen that, we use OSM Overpass API. Now, OSM stands for OpenStreetMap. This is an API which is a read-only API. It serves you custom selected parts from the OpenStreetMap. What it does is basically you can specify whether you want a road map, water body, or anything else which is of relevance, like a highway or a motorway, and it will give you back those details. So with this Overpass API and using the coordinates that we got from the previous process, we identify the road infrastructure and around infrastructure, basically the highways which are there. And then we use a tool called as XCube, which is a Python-based library, which then allows you to extract the Sentinel-5P images across time. Okay, so it's create a cube of these satellite images. And here, what we are doing is that we are providing one dataset name that we want, which is basically, it means S2 means Sentinel-2, L2A, which is a kind of normalization that we do on the Sentinel-2 images. Then we specify the bands that we want. It's the B02, B03, B04, 8, 11, and SCL. So over here, B02, B03, they stand for the blue, green, and red bands, while B8 stands for the infrared. and B11 for short wave. SCL stands for scene classification map. And we specify the tile size, the geometry, which is a box size, the spatial resolution. So we can specify the different resolutions out there. So we specify that we want a minimum resolution, which is good for our use case. And then we specify what is the time range over which we want it. So this the output is a cube with each layer containing one satellite images from across the time period. And then we have to do some processing on that where we try to calculate these values. We calculate the values to identify the reflectance. We place a mask on top of it. We have the OSM, which is the road network. So we use that as a mask to just get the areas of interest, and then we calculate all the using calculate number of trucks out there. This is basically is like we are first trying to do a negative action on that. First, remove all vegetation, remove all water bodies, remove the snow, and then we are calculating the blue-green ratio and the blue-red ratio to find this kind of a rainbow reflectance. And then we identify those reflectance which has taken place on a highway or a motorway, and this helps us. This basically gives us one single pixel, which we rasterize just so that we can plot it. So 1 or 2 pixels will indicate one truck out there. Then we can then use this information to plot it out. For Visakhapatnam, we show that there was a significant, almost a 20% drop in vehicular traffic, container traffic across it. So this is our first use case. The second use case, and this we can actually do for multiple ROIs. You can do it across the entire planet and major container shipping ports, and then we can identify the changes in transport. The other use case that we will cover more in detail is about surface water monitoring. And here we are using the NDWI index to calculate the changes in surface water. And we have used two very beautiful tools out here. And one of them is Google Earth Engine, which is a cloud computing platform for processing satellite images and other geospatial and observation data. It provides access to a large set of database satellite imagery, and also the computation power through the GCP cloud infra, which is needed to analyze these images. You can also have a Python and a JavaScript API, which makes it easy for you to use it. Another resource that we have is GMap, which is a Python wrapper across the Google Earth Engine API, and which also uses IPyLeft and IPyWidget, which is integrated with the Earth Engine, and so you can use it in a Jupyter notebook. So if you're interested in geo mapping and analyzing satellite, I highly suggest looking at gmap.org. So using these tools, what we have done is we have calculated the NDWI index, which is a normalized difference water index. It basically takes two bands, which is band 3 and band 6. Now, why do we use that? Is basically water bodies can absorb light in the visible to infrared magnetic spectrum. So green and short wave infrared waves can be used to actually calculate, to identify what surface water. And for Landsat 8, which is one of the oldest satellites in orbit, band 3 and band 6 provide those values. So by using this, the equation that you see on the top left, we are calculating the presence of water bodies in the images. Mostly NDWI values takes between -1 to 1, and generally if the value is about 0.2 or 0.3, we can take the assumption that it's a water body, a surface water body. So let me start. So what we do is we have created a widget, a Jupyter widget, where you can zoom on in any location that you want is of interest. You can select a box across it. And once you select a box, it will create a layer on top, which is the NDWI index layer. where the blue color, the greater the blue color, which it means that it could be a water body. So, and then what we do is that we take count the number of pixels in these which are close together. Uh, then we multiply it by the spatial resolution, which gives you the area. And using that, we can plot out the temporal trend across between from say January to May. Um, as you can see that from January, which is the winter months in India, to May, which becomes midsummer, there is a drop in surface water, which might make sense. The second thing that we did was using this system called as connected component analysis, which is part of Open's any computer vision library. We try to calculate a number of water bodies which are there. So here we have selected in the first, you see the selection of the water bodies. And then after identifying the NDWI index, we do some processing, which is basically converting to grayscale and doing some smoothing to reduce the high frequency noise. We threshold the image and we get the one you see on the right side, which is white and black, where the white indicates a water body. And then we use a connected component analysis to identify what can count the number of them. So whatever is close together, we identify as a large blob. And once something is identified as a large blob, we count it as one as a water body. Now, the disadvantage of this is, of course, that if it is smaller than a certain threshold, you won't be able to count it. And if it has irregular shapes, sometimes irregular shapes can result in inaccuracy in calculating the area. So also, sometimes we might miss out because of construction. We might miss out some of the counting some of the water bodies.